this thing on? Yes, yes, this thing is on. Greetings, welcome, and good evening. Welcome once again to your favorite class. Yay. How's everybody doing today? Brilliant. Excellent. Brilliant as the shining white diamonds of the Northwest Territories, I'm sure. So, I had a look at the petitions that were made over the various questions on the quiz, and I sort of, in post adjusted a few of the answers. Some of them were actually wrong, which is incorrect to say the least. Others, it was kind of like, well, was this question really fair? So I gave out some free marks, and that increased the average from 60 to 66 to 72. So I think 72 is an average I know I'm happy with. Hopefully everybody else is happy with it as well, and we can hope for similar averages going forward, maybe even higher. But yeah, any questions about any of that before we, any lingering, yes?
Yeah, did you give out marks individually or per question in the
If you got one of the questions that I corrected, then you got the change. Yeah, it wasn't like a blanket effect. So, yeah. So anyway, let's continue on with our discussion that we were having on the subject of analog and digital signals, which the more I make these slides, the more these are turning into analog, digital, and signal processing slides. Yes?
Could you post these slides to Avenue?
I think I did like 5 minutes ago. Yeah. If you haven't checked in the last 20 minutes, I believe I uploaded the latest version right before I came over here, so. Because guess what I was doing right before I came over here?
Writing them?
I was writing them, that's right. Notice we have 36 of them now. But anyway, so, yeah. That's for the memes. So, last time we were talking, we were basically mostly just motivating the idea that we need analog to digital conversion. One of the more important points that we covered was this idea that when we take samples from an analog signal, we have to sample them and we also have to hold that signal for the duration of that sampling period so that we don't get intermediate wrong results that arise inside of the analog to digital converters. The analog to digital converter will have this built into it, but it's sort of an important conceptual point. We have to start thinking about how we move from a continuous signal to a discrete signal, and this is the first step. Make sense? So let's talk about sampling. So we have this idea of the sampling frequency, right? The frequency at which we pick samples off of an incoming analog signal. It turns out that there's a rather important result / theorem that we have to talk about with respect to sampling. So this man is Harry Nyquist. He is a Swedish-American physicist and electronic engineer, and he came up with a very famous result and a very sort of introductory result in signal processing known as the Nyquist Theorem. So, a band-limited signal of finite energy, which has no frequency components higher than W hertz, may be completely recovered from a knowledge of its samples taken at a rate greater than 2 W samples per second. So, we're going to get into this in a little bit more detail later on in this series of lectures. One of the things that I really want every one of you to take away from this series of lectures is a different way of thinking about signals, right? Because so far, the sort of natural way to think about signals is primarily in terms of amplitude, right? We have to start thinking in terms of frequency as well. So many of the analog signals that you will encounter are compounded conglomerations of several smaller signals, all at varying frequencies, right? AM and FM radio. Who can tell me what AM and FM in AM/FM radio stand for? Yes?
Amplitude modulation and frequency modulation, I think?
That's absolutely right. AM radio is amplitude modulation radio. Frequency modulation, that's FM. Which is better, AM or FM radio? FM. Much more clear sound, right? Why? Any ideas? What happens to the amplitude of a wave when it passes through, like, an obstructing interference? Yes? Attenuation. Most specifically, you get it damps down the signal and increases the noise, right? So with amplitude modulation, it's not as good at passing through solid objects. That's why amplitude AM radio, fuzzier, not as distinct, kind of more difficult to listen to. Frequency modulated radio, much more easy to listen to, because it's not like, obviously, if you lose all the amplitude, you don't have a signal anymore. But the information is contained in the frequencies, not in the amplitude, right? So that means that it's stable through things that would dampen down the amplitude. But anyway, so we need to start thinking about signals as containing many frequencies. Nyquist's theorem tells you how fast you have to sample a signal to be able to reconstruct it, right? So, for example, human voice, right? Human voice sort of maxes out, I looked this up, maxes out at about 10 kilohertz, 8 kilohertz, 8 to 10 kilohertz, right? So, according to this theorem, how fast do we have to sample that signal to be able to reconstruct human voice? Yeah?
20 kilohertz.
20 kilohertz. That's actually not that fast relative to processors, right? Like, you know, your standard, if you have a microcontroller operating at, like, you know, 20 megahertz or something like that, that's like a, you know, 3 orders of magnitude less fast than your operator, than your system's actually running. Speaking of, like, signal interference, is this microphone okay? I can just shout if this thing is, like, difficult to listen to. Is it okay? Okay. All right. So in order to be able to reconstruct the signal, you need to be sampling at least twice the highest frequency component of it that you care about, right? With signals, you'll often have higher frequencies present in the signal that you don't necessarily care about, right? This will often come up as noise, right? If you don't care about high frequency signals, then you don't care about reconstructing them. But otherwise, this is, so if I put a question on a quiz, if you're trying to reconstruct a signal with a highest frequency component of X frequency, multiply it by 2 to get the sampling rate. At least 2, right? So, the Nyquist theorem states that unless you sample at least twice the highest frequency component of the analog signal, you can't completely reconstruct it. This failure of reconstruction results in the detection of frequencies which may not even be present in the original signal. These fictional signals are known as aliases. Question for the class. Why wouldn't we just, actually, someone, where the person who asked this last time, I think you're sitting in the back. There you are. Yeah, you actually asked this question already, so good job. But Why shouldn't we just sample as fast as possible and not worry about signal reconstruction? Anybody remember what I said yesterday?
Power.
Power, yep. Yeah, basically it's wasteful, right? Yeah, and of course, one of the, as we are engineers, one of the things that we try to do is reduce waste. So, there you go. So, here is an example of the aliasing effect. Here we have displayed a series of sine waves of increasing frequency, right? This one, 200 hertz, 400 hertz, 800 hertz, and 1500 hertz. We are, however, sampling this at a fixed frequency of 1600 hertz. So, you can see with the 200 hertz signal, you get enough dots that you can perfectly reconstruct the sine wave, right? At 400 hertz, you can still reconstruct the sine wave, although it's kind of like, I hope that you know that you're looking for a sine wave at that point, but you can still reconstruct it. At 800 hertz, which is half of the sampling frequency, you can see this is kind of actually one of these interesting little cases. You get a lot of these interesting little mathematical cases on like the exact boundary lines of some of these numbers. In this case, it looks like the signal is dead, right? If you knew that this was a sine wave and you knew that these were the points at which the sine wave was intersecting the x-axis, you would be able to reconstruct from this. But, you know, if you went in with less foreknowledge, you wouldn't necessarily be able to reconstruct something from that. Yes?
Sorry, what did the dots mean again?
These are the samples that we are taking. Right? So notice that these dots are occurring at the same rate regardless of what graph, like there's the same number of dots no matter what graph you're on. So these are the points at which we are sampling the signal. Make sense? Good. Any other questions so far? Okay. Actually, can I just get you to hold on to it until I finish talking about this graph? Yeah. Okay, thank you. So, if we take a signal which is very close to the sampling frequency, you can see that when we sample this oscillation, we get a different point in that oscillation each time we sample it. And when we sample, like if we were to try to reconstruct a sine wave from these points, we get one with a very different frequency than the signal actually has. This frequency does not exist anywhere inside of this signal. This is an alias. It's actually, it's easy to make an oscilloscope do this actually. If you're giving it, well, I don't know, maybe, it's certainly easier to do it on old oscilloscopes, but like, if you have a very, very rapidly oscillating signal and you're viewing it on something like an LCD screen, you might see like these kind of phantom sine waves coming in and out of it. It's an aliasing effect, but it's an aliasing effect because of the discretization of the LCD display, right? Because it's only got so many pixels, which kind of in that sense act as sampling. It's kind of the same effect. Oh my gosh, probably this is like, oh man, I'm gonna definitely show my age when I say this one. But so the Sega Genesis, right? Some of the old racing games, like first-person racing games on the Sega Genesis, had like you would have like the road, right, going off into the distance. And you would have like these graphics of palm trees that would kind of come pop in and then go off. And you had your little guy in the middle on his motorcycle. That's a terrible diagram of a motorcycle. Anyway, so, and they would have like these little, like, checkerboard things along the side of the road in these old video games, right? If you were going fast enough, because the intention of this was to give you an impression of your speed, right? If you were going fast enough, it would look like they would stop and then they would start to look like they were going backwards. And that's an aliasing effect as well. But anyway, so this is aliasing. Any questions? Yes, sir.
So is the reason it's aliasing because it looks like a different kind of wave? Or, I'm just a bit confused what aliasing really looks like.
Right. So, if you didn't know what the original signal looked like, and you were trying to reconstruct the signal just from these samples, what kind of a frequency would you get? Would you get the small one or would you get the big one?
The big one.
Yeah. So this is the alias, right? The fact, like, the signal that you would reconstruct using these points is the alias of this signal, given that the sampling frequency isn't fast enough to reconstruct it.
Okay, so for the 800 hertz, since if we didn't know it was a sine wave, then the dead wave would be the alias.
Yeah.
Okay.
Yeah. It's a signal that isn't there, and it's an artifact of the sampling frequency.
Okay.
Make sense?
Yeah. Thank you.
Question?
So if you do not know what type of wave you're expecting, would you multiply by 4 in that case to like get more accurate result?
For this one?
The one above. You know how like we didn't know if it's sine or if it's square, but because like we don't know if it's what type of wave it is, but because it's 4 times smaller than what we're like looking at, we can detect what type of wave it is.
Yeah. So I know this is going to sound weird, but we're going to come back to this idea of like the square wave versus the triangle wave, right? When you're doing these types of analyses, you only consider sinusoidal waves because of, we've got a lot of slides on it coming up, but essentially you can construct any other periodic signal as a Fourier series. And the Fourier series is a sequence of sinusoids of varying degrees of amplitude which have been added together. So essentially, we don't have to worry about whether or not this is a square wave or although you're absolutely right. If this were like if it were a square wave, it'd be very difficult to hit these points. But yeah, it's this is kind of like a facile example to an extent because like ordinarily the frequency that you're measuring is not going to be like a perfect division of your sampling frequency. That's like a very, very rare mathematical case. So, you'll be able to do better than this. But again, we're talking about signal reconstruction. So there is always going to be some degree of mismatch, right? But, actually, now that I think about it, right? So I can answer your question more thoroughly. So square waves, right? This point right here, how high a frequency would you need to be able to achieve that? Think about this, like this straight line, this straight down segment, right? How fast would the frequency have to be going in order for a sinusoid, this section of a sinusoid, to be nearly perfectly vertical?
Very fast.
Very, very fast, right? So you would need a sampling frequency twice as fast as that to be able to reconstruct the square wave perfectly. And the fact is, like electronically, they aren't generated this perfectly either, right? So generally speaking, when you're reconstructing a sine wave, you get something that looks like something like that. And you guys, if you looked at square waves on an oscilloscope, you'll probably see something more like this, right? Yeah, so that's the real answer.
Thank you.
You're welcome. Any other questions? You in the back, sir.
Wouldn't 800 hertz be half the sampling rate? So wouldn't it be able to tell that's a sine wave?
Again, it's like when you hit these the exact barriers, you get like sometimes these mathematically weird situations. You could reconstruct this if you knew what you were looking for.
Right.
Right.
If you didn't, you would just think it's a
Exactly. It's an edge condition. It's a boundary condition. You're going to see another one of these coming up in 3DX4 where, like, if you have a system that's stable, it settles to a particular value. If you have a system that is unstable, then it blows up and moves off to infinity, like in either direction. And if you have a system which is marginally stable, it just has like a perfect oscillation whose amplitude does not change off to infinity. Very, like, almost impossible to actually hit something like that, right? But yeah, you get interesting mathematical properties at the edge cases.
So if it was like 799 hertz or something, you'd be able to reconstruct it perfectly.
Yeah, exactly. Because these, like, this dot would like come down very slightly. That one would go up very slightly, etc. And then it would like,
You could, okay.
yeah, get it? Awesome. Any other questions? Good. You guys haven't covered this stuff yet, right? This I'm not like doing review, am I? No? Okay, good. Sorry?
For the 30 years, yeah.
For the third years. Oh, yeah. You guys have taken
3MX3.
3MX3, yeah.
The IOs have their own single scores.
Yeah. Okay. How many people already knew all this? How many people didn't? Well, that's actually the majority, so given that this is a second year course, I think this is justified. I mean, technically speaking, you know? Right. So, another design consideration when you're, and this, we're kind of coming back to analog to digital control. Another design consideration of analog to digital converters is the resolution of the resulting digital signal. We touched on this briefly last time. So, resolution in this context is the number of unique values which can be represented, which of course is 2 to the power of n, where n is the bit width of the digital signal. When you see digital, analog to digital converters advertised, this is often the most important metric that it accompanies the name of the part, or like you don't even need the name of the part, you just say, I have a 18-bit, I have an 11-bit analog to digital converter, right? So, we can calculate the voltage difference between adjacent unique values using the following formula. So, if we're going from 0 to some reference voltage Vref, if you take that and you divide by 2 to the power of the number of bits you have, that is your voltage quantum. That is the smallest, like, it's in, like, okay, let me see. Right? So, if you have like 5 volts and you have 0 volts, right? If you have 1 bit, you can do 0 or 5, right? If you have 2 bits, you can represent these levels, right? Each bit that you add increases the division of the signal, right? This guy right here, this is VQ. Okay? Make sense? Good. Basically, this is the resolution of your analog to digital conversion. You cannot measure any change in voltage smaller than this using this method. So, if you need to measure very, very, very small changes in voltage, you have one of 2 options. You either get an ABC which has more bits, or you amplify the signal, as you guys are finding out. Make sense? Good. So, I think I already showed you this because it's this interactive tool game. But if I pull down the frequency a little bit, there we go. So, as you increase the number of bits, yeah, this doesn't, yeah. you can see that the steps become more precisely aligned to the signal at the points at which the sample is being taken. Make sense? Good. So, now that we've covered all of that, let's talk about some actual analog to digital conversion technologies. We're going to talk about 3 different technologies, actually in the reverse of the order presented on this slide. We're going to talk about sigma delta, or delta sigma. I've seen it done both ways in different sources. So delta, like you can, yeah, oops, should have. Delta sigma, sigma delta. Strike that, reverse it. Thank you. So, we also have the successive approximation register, or SAR, and we have flash analog to digital conversion. Delta sigma reads signal change and adds it to a running total. This is a very rough approximation of how it works. It works well for high-resolution, low-frequency applications, such as human voice, commonly used in cell phones for voice acquisition. One of the huge advantages of the sigma delta is that the circuit size is very, very small. It's very miniaturizable. However, the science behind how it works is also very complicated and not easy to understand, and actually more appropriate for one of those signal processing courses that we were mentioning. The successive approximation register performs binary search over the possible voltage range. It's the low power consumption option for medium frequency signals, something less than 5 megahertz. It's ideal for devices with tiny little batteries. So, for example, the new Fitbit that measures your, or I guess it's the old Fitbit now, but the one that measures your pulse, right? That would be an analog signal that they're measuring there from the transducer. Because the Fitbit has very high battery life requirements because it's a watch, this is probably the one that they would be using there. It's also reasonably small relative. Like flash is like, well, it's kind of flashy. It's very large, but also very fast, right? So flash ADC uses an array of comparators, all at the same time, large size, large power consumption, and low resolution, for reasons we're going to see. This is the fastest of all of these technologies, and it's used in such applications as oscilloscopes and radar communication. So, again, when you need very, very high frequency analog to digital conversion at some expense, you use flash ADC. So let's examine flash ADC first. So, we have a string of resistors on this side which function as a successive division of this voltage, right? Each one of these different points is represents one of the voltages that you're dividing into your bits, right? So comparators, these comparators, we actually have a slide on them next, but what they do is they compare the incoming voltage signal to the reference voltage which is generated by the resistor string, right? The point at which this flips from 0 to 1 indicates which of these different voltages this guy matches most closely. At that point, we can take the input from all of these comparators, run it through some digital logic, and determine our digital output. Does that make sense? Question?
So what would the bit width be for this example?
3.
3?
Yeah. So we have a bit width of 3, and we have 7 comparators. So the number of comparators that you need according to this method is 2 to the power of the number of bits that you're outputting. So you can see why this is the expensive option, right? So let's talk about comparators for a moment, right? Have you guys haven't done comparators, right? Am I, no? Okay, good. So we should, since the comparator is an essential component of analog to digital conversion, it is worth our time to just dwell on them for a moment. So, a comparator receives 2 analog signals, the input voltage signal and a reference signal, and it outputs 1 digital signal. This is kind of like the workhorse of analog to digital conversion. This is the place where an analog signal becomes a digital signal, right? So, if Vin is greater than the reference voltage, this thing outputs high, otherwise it outputs low. So, if this is the incoming signal, once it passes Vref, then you get a high signal, and when it goes below it again, you get a low signal. So this is using a differential amplifier, not an operational amplifier, in case you're interested in the difference between those. Apparently, you can make a comparator out of an operational amplifier, but it's like more than you need. These are a bit simpler, you know? So, yeah. Any questions about that? Cool. Question?
So in the previous slide, wouldn't Vref always be lower than?
So Vin here is the incoming analog signal, right? It could be 0.2, it could be 1.5, it could be anything inside of that range, right? Make sense? Any other questions? Good. So how does this thing work? A resistor ladder sets up a series of reference voltages, each separated by the ADC's voltage quantum. The input signal is compared to each of these reference voltages. The comparator outputs will show which reference voltage level is closest to without going over the input signal. Price is Right rules. This can then be converted to a binary integer using digital logic. So, pros. This can be done in 1 clock cycle. Cons. This takes 2 to the power of n minus 1 amplifiers, where n, or comparators, where n is the bit resolution of the output. So, for example, if you wanted to make an 18-bit analog to digital converter using this method, you would need over 250,000 amplifiers. So, you know, you're not necessarily looking at civilian applications for something like that. Question?
So is it comparators or amplifiers, or are they the same thing, basically?
The core of a comparator is an amplifier, a differential amplifier.
Okay.
Yeah. Any other questions? Cool. So that's all I have to say about the flash ADC. We'll move right along now to the successive approximation algorithm and setup. So, in this case, we have our incoming voltage signal. This is the analog signal coming in. In this diagram, it's being run through a sample and hold circuit explicitly. That was implicit in the last one that had already been sampled and held. We have one comparator. We have the successive approximation register right here. And interestingly enough, we have a digital to analog converter inside of our analog to digital converter. And I assure you, digital to analog converters do not require analog to digital converters, so we're not talking about like an infinite regression of converters, converting converters all the way off to infinity, turtles all the way down, as it were. So, this is how it works. We start with the most significant bit. We set that bit inside of the SAR. We take the value of this register, convert it to a digital, or convert that digital signal to an analog signal and compare it to the incoming voltage. If this voltage is greater than that, we keep the bit. Otherwise, we set it to 0. In both events, we then move on to the next bit and perform the same process, keeping the state of the previously found bit. What this ends up doing is it performs what looks like a binary search over the entire signal. Now, remind me, did we talk about binary search in 2MP3? I'm getting some nods. We get some yes. Okay, good. So, I have a graph of this. So, over time, this creates a closer and closer approximation of V in. By the time you have done all of the bits, you get a value as close as possible to the input value. But if you really wanted to, you could stop this thing after, n bits and get, an n-bit approximation of the actual voltage value. So, here's an example of this algorithm in operation. Let's say we have a voltage signal V in at somewhere between half and a quarter of the reference voltage. Right? First step, we set the first bit, the most significant bit, to a 1, convert that to an analog signal. That brings us here. We compare these two using a comparator. This is greater than the input voltage, so we discard that bit. We set it, we keep it as a 0. We then move on to the next bit, set it to 1. That corresponds to a voltage level of 1/4. That is less than the voltage that we're trying to measure, so we keep this bit. We set it, we leave it as a 1, and we move on to the next bit. We set this bit equal to 1, we compare the two signals. This setting it to 1 made it greater, so we discard that bit, we set it equal to 0, and we move on to the next bit, and you guys get the point. Does that make sense? You guys must be understanding this pretty well, because I'm not getting a huge number of questions relative to the number of questions I usually get. Yes?
So the sample and hold thing that you have, does that hold numerous bits, and then you have to have some way of communicating to it to tell us which bit you want to read and compare?
No, the sample and hold is just doing, it's just doing this process, right? So, at the sampling frequency, it takes whatever the voltage is currently and holds it at that voltage until the next sample comes in. Yeah, it's still analog, yeah. But we've discretized it by time rather than by bits, right? So yeah, sample it, hold it, and that way this, like, the sample and the hold allows us to perform the conversion without having to worry about the input signal changing mid-conversion. Makes sense. Good. Any other questions? Okay. Good. Where were we? Yeah. Good. So, sigma delta. Sigma delta is very complicated, and it requires more knowledge of signal processing than is prerequisite for this class. But here is a rough overview. essentially, like, to actually like fully understand how this thing works, you'd probably have to be like at least like a third year in like the electrical engineering stream or some stream that focuses specifically on this stuff, you know? But anyway, so the first step in sigma delta is delta modulation. So rather than directly measuring the voltage of the incoming signal, what we're doing is we're comparing the signal to its previous state or its previous value. So we are in effect measuring the delta. We are measuring the difference in the signal. The next, so that gets you so far. The next thing that you have to do in a sigma delta is you must sum that difference back into the original signal before the delta modulation step. This improves the accuracy of the entire apparatus. So delta, you find the difference. Sigma, you calculate the sum. And then you keep processing it that way. It kind of just spits bits out at you one at a time. So this is what a block diagram for that looks like. I don't expect you guys to like memorize it or anything. So we have a difference amplifier, we have an integrator, and we have a comparator, all in this circuit. We then also have a 1-bit digital to analog converter. This signal goes off to be filtered a bit more, and that's what pops the bits out. So, if you'd like to do some additional reading on this, just, you know, in case you're you have to be like a pretty nerdy person to be in this class to begin with. But if you're like the lizard king of nerds, you could read this article if you want. I'm not going to be quizzing on it. It won't be on the test. But it's like, although the mathematics is highly advanced, this is like a very commonly used ADC module, so we need to talk about it. So here's what's important to know. While it may not be the fastest, sigma delta circuits are very small. SAR beats it for power consumption, but sigma delta takes up much less space. The digital to analog conversion module inside of that actually takes up more space than you might think. To human beings. Any questions? Good. All right. You guys don't have any questions because this is all being understood, right? You're not like lost, right? Okay. All right. I never know, you know, I have to ask. So, good. So now that we've talked about analog to digital, let's talk about digital to analog. So, in comparison to analog to digital to analog is simpler to understand. It's more electrical and less, there's a register here that's doing God only knows what. So there are 3 primary methods that we'll be talking about in this class. Pulse width modulation and filtering, which we have talked about pulse width modulation before, but what's wrong with the camera?
Battery dead.
Battery is dead. Oh,
It's okay.
How long has that been? Oh, you're recording on your phone?
Yep.
Okay. Well, this will be an interesting video. Thank you for jumping in with that. You know what it was? I left the charging cable here like yesterday, and thank God it was still here, because I was looking on Amazon and they're like, it's like $10 for the cable, but $15 for the shipping, and it's like, but you could literally just put it in an envelope. But anyway. So, PWM and filtering. resistor ladder and resistor string. This is actually reasonably similar to the resistor string that went into the flash ADC. So, with PWM, doesn't actually require a DAC module, but it's also not suitable for high frequency signals, as we're going to see. Resistor ladder, digital bits drive voltage directly through a series of resistors, requires fewer resistors, and then the resistor string, digital bits drive transistors which pick voltage from a resistor string, requires 2 to the power of n resistors. Good. So, PWM. We've talked about pulse width modulation quite a lot, right? As we know, the average voltage, if you were to calculate the average over time, you get basically the duty cycle of the pulse width modulated signal, right? In this example here, we produce a sinusoidal average value. The blue here is on and the white is off. So the average, like if you took the average over, the 5 or 7 adjacent, surrounding it, then, although you have to do it back because you can't look forward in time because of causality. But yes, it's important, as great as the temptation is, it's important not to violate the laws of causality with your electronic circuits. Cause must precede effect. But anyway, so in this example, we produce a sinusoid. Question remains, however, how do we take this series of pulses and extract from it an average voltage? And I think that's a good place to leave it for today, actually, because the next has a picture of the ear on it. So thank you very much for your time and attention, folks. We'll see you all on Monday.